Hello everyone, this is our lecture on Ohm's Law. Before we start doing anything, I want to review a few things from the last lecture. So here are a few key definitions and key points from the last lecture. Electric current is a flow of charge. Voltage is the force that makes the current move. And resistance is a measure of opposition to the current. In other words, it resists the current and it can be measurable. Now, for the purposes of this lecture and for really the rest of the class and most likely the rest of your life, if you're going to do electricity and electronics, voltage is denoted by letter V, current is denoted by letter I, and resistance is letter R. Okay? So when you look back at our previous lecture, you will remember that as you increase voltage, you increase current. So the question is, how can we write that down mathematically? And how can we express that in words? And this relationship is very special because it only works one way when you get down to it. It is true that if your current has increased, you probably have increased the voltage. But you can also change your voltage without increasing your current at all. You can have your voltage without having any current. So how do we write this down? So this is how this looks like. Current is directly proportional to voltage. In other words, what does this really mean? This means that if voltage goes up, then current also has to go up. This is what it means. And mathematically, we cannot put an equal sign between them, right? Because they really are not. But we can say this, that voltage is proportional and current are proportional. So this looks like a similarity symbol when you did your geometry. That's because if they are related by some kind of ratio, that ratio should be unchanged. Of course, they're not related by ratio, but they're still proportional. Okay. So next one. Current is also proportional to resistance, but it's not directly proportional. If you think about it, when you increase your resistance, the current has to slow down. So the relationship is completely opposite of what it is with voltage. Remember, with voltage, if you increase the voltage, the current has to go up. But with resistance, it's the other way around. You increase resistance and the current goes down. So that is inverse proportionality. So current is inversely proportional to resistance. And like I said, if resistance goes up, then the current has to go down, right? The current has to go down. So mathematically, this looks like current is proportional to 1 over R. Well, proportionality is not going to do us much, right? We need an equality. We need something that can give us an nice equal sign. And turns out that when we merge both of these expressions together, we get what is called Ohm's law. And that is a relationship that actually has a equal sign in it. And this is the Ohm's law. Current equals voltage over resistance. Very, very, very simple. Now, the next thing we need to do is we need to figure out what is going on really when we're talking about voltage, current, and resistance in this case, and what kind of voltage, current, and resistance are these? When we're talking about an Ohm's law, we're talking about a circuit element. Our circuits consist of all sorts of elements. We have diodes, we have resistors, we have capacitors, we have transistors. Almost all of them have resistance of some sort. So all of them will have R. If we're using that circuit element, it makes sense that we will have a current flowing through it. And then, of course, there is voltage. And voltage will be energy that is lost while passing through that circuit component. So here's my example. This, and let me draw this properly. This is a symbol for a resistor. This is resistor. Okay, so this is a circuit element symbol for a resistor. So we're going to have a current coming in through it, and the resistor is going to have some kind of resistance. So it's going to resist the current, and while it's resisting the current is trying to push through, the current is going to lose some energy. If you guys remember this picture that I drew for you last time, right? So I have a bunch of copper atoms, right, in my wire. And I have a bunch of electrons passing through as well. And my electrons can pass through almost unimpeded. In other words, there is almost nothing blocking them. There is virtually no resistance in the wire, especially when we're talking about the current flowing over short distances. But what if we change the material, the composition of our wire? So now I have a whole bunch of atoms over here. Now I don't know what they're made of, but I have a lot of them. They're all over the place. And this thing doesn't want to draw. Well, remember what I showed you last time, right? My electrons are going to start bouncing inside that material. They're going to bounce off one atom, and they're going to bounce off the other, then the third one. Eventually, they will get through, but as they bounce inside that resistor, they are going to lose energy. Now, if you guys remember, voltage is energy per charge, right? Literally, our measurement of voltage and our units of voltage is how much energy does each electron have. So since all electrons are passing through exactly the same resistor, they're all going to lose the same amount of charge, which brings me to our definition of a voltage drop. Voltage drop is the amount of voltage and I'm going to put energy in parentheses because voltage really is energy lost when electrons pass through a resistor. Or really any other circuit element. So this is what voltage drop is. It's the amount of energy lost. Okay? And this is what our Ohm's law gives us. The current in this formula is a current that passes through a resistor voltage is the voltage drop. And resistance is, of course, the resistance of the resistor. All right. So this is really all there is to know about the theoretical side of Ohm's law. So next, I'm going to do several problems showing you how to solve for practical side of Ohm's law. In other words, how to use this formula. I'm going to do it in the next lecture video.